So we're going to look at a very sort of brief video of some of the topics in chapter 13 to get you started on some of those practice problems. Okay, so first, chapter 13 deals with properties of solution and what happens to a lot of the physical properties when we create a solution. So first, let's look at the energy of creating a solution. So we essentially have three different things that happen when we make a solution. So the first thing is we have our solute. So again, you can kind of think of it as salt, for example. So the first thing we have to do is break those interactions that are holding the solute particles together. Okay, so again, for an ionic compound, that would be like the lattice energy. So we'd have to break apart those sodium and those chloride ions. If we had a polar compound, like for example water, we would have to break apart those interactions like the hydrogen bonding in water, or again, if you had something else like a dipole-dipole force or something like that. Okay, so we are breaking these interactions, and interactions are kind of like very, very weak bonds. So this requires energy to do. This is an endothermic process. Okay, so we have to repeat this process with our solvent. So whatever our solvent happens to be, we have to break those solvent-solvent interactions. And again, could be dipole-dipole, hydrogen bonds, dispersion forces, whatever they happen to be, we need to kind of break those interactions to make a solution. So this is also positive. Okay, so finally, once we make our solution, we are forming new interactions between the solute and the solvent. Okay, so kind of forming bonds. So this is exothermic. Okay, so again, if it's a ionic compound into water, we're forming ion dipole forces. If you're dissolving something like alcohol into water, both which are polar, you can get dipole-dipole, or again something with that would give you hydrogen bonding, again something like that. Okay, so two processes that are positive, breaking interactions, and one that is negative. So the energy for, or your enthalpy of forming a solution is all three of those things added together. So these two are positive and this one is negative. So to form a solution, so to get something to dissolve into something else to form a solution, generally speaking, we need delta H to be negative. So we need the solution to be at a lower energy state, to have a negative delta H to get our solution. So what that means is this term here, which is our only negative one, would have to be larger than these two here. Okay, so that negative energy here has to be larger than those positive energies there. So then we'll have, again, a negative delta H, and generally speaking, a solution will form. If this is positive, meaning these things are being held together by very, very strong forces, so these are large and positive, and this isn't enough to overcome, we have a positive delta H of solution, and generally speaking, a solution will not form. And so there are, of course, situations where if you get a positive delta H, we still form a solution. And that other factor that we're not going to talk about a whole lot in this class is something called entropy. So entropy is the measure of a disorder of a system. So in the universe, things tend to move towards more disorder. So again, what that means is a very structured, ordered, something like a solid has low entropy. Something random with a lot of movement like a gas has high entropy. And again, things tend to proceed in such a way that the entropy of the universe is increasing. Okay, so if you kind of think about forming a solution, your solid is nice and ordered and packed together in these crystal lattice structures, very, very ordered, very low entropy. And even something like water with its hydrogen bond forming these kind of angles and stuff like that in solution, also pretty ordered. When you mix those together, you are taking that very structured crystalline lattice and breaking it apart and forming something new. So you are increasing the entropy of the system, again dissolving things in, by breaking up all that order and structure in that lattice structure of that solid. So we can get a solution that forms if we have a very large increase in entropy. We can, again, have a particular solid that would dissolve into water. Okay, so kind of to sum all of this together, this all seems kind of complicated. I mean, it's not too terrible, but we have something that is a really, really nice sort of recap of all of this that kind of will be a good rule of thumb for when making a solution. So generally speaking, you can get this to be nice and negative if you're trying to dissolve like into like. So we call it like dissolves like. Okay, so things that are polar dissolve well into other things that are polar because you get a very large negative term here. Things that are ionic dissolve well into other things that are, charged like a polar substance. So you get that large ion dipole term here. This would be nice and negative also. Okay, so the other part of the like dissolves like is the nonpolar. So all of these are pretty small for something that is nonpolar. They're held together all by dispersion forces. So when we're looking at something like a nonpolar substance, the entropy is going to be a much larger factor, where you're increasing the disorder of that system by having a random mixture of your solute and your solvent all in together in the solution. Okay, so like dissolves like. For ionic and dipole, we get a very large term here. And again, for nonpolar, the entropy part of that is going to be larger. Okay. So next we are going to look at what's called saturation. Okay, so we can only put so much of a solute into solution. Okay, so we have what's called saturation. Saturation, if a solution is saturated, we've dissolved the maximum amount of solute in solution. And this forms what's called an equilibrium system. In an equilibrium system, you have things occurring in one direction at the same rate that they're occurring in another. So in a saturated solution, you have your solid particles dissolving into solution at the same rate as your particles are coming out of solution and crystallizing or precipitating out. Okay, so this arrow and this arrow are occurring at the same rate. Okay, and what that means is over time, the amount of solid that has been dissolved into solution doesn't change over time. Okay, so we've put the maximum amount in there. So saturation is very much temperature dependent, and we're going to see this. So as temperature increases or decreases, the amount of solid that we can dissolve into a liquid does change. Okay, so we also define something called solubility. We looked at this a little bit in chapter 4, where we said things were soluble or insoluble. So soluble things had a large amount of solid dissolved, and insoluble things had a very, very small amount. But we can quantify solubility and talk about the pretty much exact amount of solute that can dissolve into a given amount of solvents. Okay, so we can say the solubility of a particular thing is, for example, 90 grams of the solute would dissolve in 100 grams of water. So the solubility would be 90 grams per 100 grams. Okay, so this is something we can determine experimentally, and we see that here. This is a figure from your book where we look at how things, how the solubility of a handful of particular solids changes with temperature. Okay, so if you look at all of them, for the most part, as temperature goes up, solubility tends to go up as well. And that is just because you have more kinetic energy in your water at higher temperatures to help break those solvent bonds and those solute bonds, so you can get more into solution, okay, because you have more energy for those endothermic processes. Okay, so for example, let's look at NaCl. So this is all in terms of 100 grams of water. So at room temperature, we'll say about 20 degrees Celsius, what is the solubility of sodium chloride? If we look up, this line right here represents the solubility of NaCl. So if we go up to 20 and we land here, we're about halfway between 30 and 40. It looks to be about 35. Okay, so what that means is at 20 degrees Celsius, we can dissolve about 35 grams of salt into 100 grams of water. Okay, so that's 35, again, we're saying as our estimate there. So what happens if we dissolve less? If we dissolve exactly 35 and are on this line, we've created what's called a saturated solution. If we are below that, so if we dissolved, say, only 20 grams, then we would have an unsaturated solution. So that means more could be added. Okay, we also have instances where we could dissolve an amount of something at a higher temperature, let it cool very, very slowly without moving it, and create something up here, like if we dissolved 40 grams of NaCl. Okay, that's called a super saturated solution. And a super saturated solution, if you bump it or put a little piece of sand or solid in there, you would see any amount of that substance above the saturation limit would precipitate or crystallize out of solution. So it's called a seed crystal. So you might have had experience with this if you've ever made rock candy. You heat up your sugar water super duper 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 hot to get a super saturated solution of sugar in water, and then you put something in there to seed the crystallization, like a string or a stick or something like that, and then those crystals start to grow on there, and they will continue to grow on there until that sugar reaches its solubility, okay, when it creates that equilibrium system of soluble. Okay, so again, looking at NaCl, it does change, or solubility does change with temperature. So at 20, let's say we were closer to, say, the boiling point of water at 100. If we look here, then we could dissolve 40 grams of salt into a boiling water solution, boiling water, so temperature of 100. Okay, so this changes a very little, but if we look at something like lead nitrate, the solubility of this one, that slope of that line is very, very sharp. So that has a huge effect on temperature. So at room temperature, we could dissolve about 55, but if we just double the temperature to 40, we're dissolving like 75. Okay, so we have a very, very sharp sort of change in solubility with temperature with something like lead nitrate there. Okay, so again, solubility does change with temperature. Anything below the line is unsaturated. The perfect amount to put in solution to get it all dissolved, that's our saturation, that's on the line. Anything above that, again, would be super saturated. Okay. So next we're going to start looking at different solubility. So first we're going to look at the solubility of a gas. So we kind of saw those plots with the solubility of a solid. Let's look at a gas. Solubility of a gas is equal to what's called a Henry's law constant times the partial pressure of the gas above the liquid. So we say S of the gas, the solubility in moles per liter, equals constant, again, which would be given to you or is in a table in your textbook, times the partial pressure of the gas above the liquid. Okay, so how much gas we can get to dissolve into a liquid depends on its pressure above the liquid. Okay, so the example we are going to look at here is the concentration or the solubility of CO2 if we have an increased pressure of CO2 of 2.5 atmospheres. And at this given temperature, our K is 3.4 times 10 to the minus 2 moles per liter atmospheres. Okay, so having an increased pressure of, say, like 2.5 atmospheres would be like creating a pressurized soda. So when you open a bottle or a can of soda, you have that sudden release of pressure because to get the CO2 to dissolve and give you the bubbles in soda, it has to have a pretty high pressure above the liquid to keep that gas in solution. Okay, so when we have a pressure of 2.5, which again, pretty typical of a can or a bottle of soda, how much of the CO2 is actually in our drink? So again, we just use Henry's law here. We're finding S. We're going to plug in our K, our constant, again, in a table or given to us, and then the pressure of the gas, 2.5 atmospheres. So atmospheres cancel and we get moles per liter, which is the units of concentration. So multiply through. Our concentration of CO2 is only 0.085 molar. But again, very nice and bubbly and makes the soda taste really nice. Okay, so again, solubility of a gas is dependent on the pressure of the gas above the liquid. So you can think of how this would be if they just let it be at regular room temperature. The amount of CO2 in here would be less than half of this, and we wouldn't get those bubbles that make our soda taste quite so nice. Okay, so directly proportional to the pressure. All right, so next we're going to look at some different now formulas for looking at a solution. Okay, so we are going to look at the chapter 13 equations. So this is in the module. So the first one we have Henry's law, which we just looked at. So we're going to skip to this section here. Okay, so we can also describe a solution. Again, so these ones are all going to express something regarding the solute to either the solution or the solvent. So the first one is mass percent. So a mass percent is your mass of solute over mass of solution times 100%. So you could have something like a 50% by mass solution. So your solute would constitute half of the mass of that solution. So another way we can express a concentration is as what's called a mole fraction. So you can have moles of solute or solvent, depending on what you're looking at, divided by the total moles of solution. So this is also kind of like a percent, but a percent in terms of moles. We just left off the multiplying it by 100%. So this is more like a fractional abundance type of thing. Okay, but still kind of the same thing, part over the whole thing. Okay, this one hopefully we're very intimately familiar with, molarity, moles per liter of solution. And now we're going to introduce something called molality. So molality is moles of solute, and now we're dividing it by kilograms of solvent. So instead of having a volume, we're looking at the mass of solvent. So why molality is used quite a bit is because the mass of a solution doesn't change. You can change the temperature, you can change the pressure, you can change all sorts of things, and the molality will always stay constant because it's in terms of amount of solute and mass of solvent. So anytime there's a phase change, molality is often used because, again, it does remain constant through a phase change. So again, think about taking a liquid and boiling it to a gas. The volume of your liquid is going to be much, much smaller compared to your volume of gas. So your molarity would change during that process, but your molality would remain constant. So again, this is often used during phase changes. So this is an M here. I usually write it, I'm going to alter this a little bit, as an M with a very scripty tail here to not get confused with mass. Okay, so we'll come back to 6, 7, and 8. Right now, we're just going to look at how these ones here are used. Okay, so shouldn't be too bad because we are, again, very used to this, and it's just slight variations of that. All right, so in that, we are going to look at this practice problem here. So for this one, we are given an aqueous solution of NaCl that is 27% by mass and has a density of 1.2 grams per milliliter. So we're going to use some of our new things. We're going to calculate the mole fraction, the molarity, and the molality. Okay, so for all of these, we're going to need different combinations of having mass or moles of something. Okay, so they didn't tell us how much of the solution we have, but the mole fraction, molarity, and molality is going to remain constant no matter how much we have. So we could have, say, 100 milliliters of solution. We could have 100 grams of solution. We could have, 1 milliliter. It doesn't matter what we have because we are looking at a ratio of solute to solvent or solute to solution. So no matter what volume or mass of that solution we have, all three of those quantities would remain constant. Okay, so we're going to use the fun trick that we used previous when we were looking at empirical formulas. When we have something by mass, we assume that we have 100 grams. So if I use my percent by mass formula, so if we use our percent by mass, mass solute, mass solution, 100%. So my percent, my 27% given in the problem, equals X grams of salt over, again, we're going to assume 100 grams of solution times 100%. That means that we're going to have for every 100 grams of solution, 27 grams of it are NaCl. For every 100 grams of solution, that means 73 grams are water, and then the whole entire total thing of solution is 100 grams. Okay, so again, I chose 100 to make the math easier. We could have put any value here to solve for x and then get these three values. Okay, so now we have mass of solute, mass of solvent, and mass of solution. All right, so the first one asks for a mole fraction. Okay, so mole fraction. So first we're going to take the grams of NaCl, turn it into moles. Easy enough. We're going to repeat that now with water. 73 grams of water, divide by the molar mass of water to get moles of water. So now we have moles of solute, moles of solvent. So our mole fraction is we're going to take our moles of solute divided by the total moles of solution. And so mole fraction is given by a giant X. So X can represent mole fraction. So our solute here, our combination of the two here, so this is our total moles, gives us a mole fraction of 0.10. So what this essentially means is about 10% of the solution in terms of amount or moles is salt, and 90% of the solution, again by amount or moles, is water. Okay, so that's what a mole fraction. It's almost, again, like a percent in terms of amount because we're looking at moles. Okay, so the next one is molarity. So hopefully, like, we're intimately aware of molarity and how that works. So for molarity, I need volume of solution. Okay, so it's moles per volume in liters of solution. Okay, so again, we assume there were 100 grams of solution. So I want to turn this into a volume, so I'm going to divide that by the density. So grams cancels. I'm left with milliliters. Again, molarity, we need it to be in liters, so turn those milliliters into liters. So that 100 gram solution by volume is 0.0833 liters. Okay, so again, using the density and converting that to liters. All right, so we have moles. We just solved for that in problem 1, the 0.4615. We have volume now in liters, so now we can just calculate the molarity there. Okay, so take our moles, again solved for in the first part of this problem and divided by our volume of solution there. So 5.54 molar solution. All right, the last one is molality. And again, we have most of the pieces already. We just have to turn the mass of our solvent into kilograms. Okay, so we had 73 grams of water, and we're just going to turn that into kilograms by dividing by 1,000. And then for molality, moles, which we solved for in the first part, divided by our mass in kilograms. So in terms of molality, 6.3 mole solution. Okay, so generally speaking, your molarity and your molality are often pretty close together because in most aqueous solutions, your density doesn't vary very much from 1. All right, so again, molarity and molality often are pretty close together because again, your density will vary. Again, we went from density of water usually being about 1 to a little bit higher at 1.2. So because the density did change, these are a little bit different, but they should generally speaking be close together because the density of water doesn't change significantly. Okay, so that is that. So these take a little bit of practice, but if you kind of have your formula sheet in front of you here, it's kind of just a little bit of a plug and chug. And again, depending on what they have you start with, you might have to do a couple of things to get the information you need. But you can get solve for any of these things if between one another. You just have to be able to make sure you can get your masses and your volume. So you might have to use the density like we did in this problem. You might have to do some assuming if you're given the mass percent like we did with that 100 grams. And you're really just doing a lot of grams to moles, moles to grams, and then again using density sometimes to go between volumes and masses. We have mass here, we have volume here, so oftentimes density is used. Okay, so that's a good one to get you kind of started on those. All right, so the next part of this chapter looks at what are called colligative properties. So colligative properties. So colligative properties are just looking at what has changed for a particular pure solvent now that we've added a solute to it. Okay, so the first colligative property is the vapor pressure of the liquid is lowered. Okay, so in my little drawing here, we have a container of water, and into it we put some salt. Okay, so at a given temperature, a certain number of gas particles have enough energy to break the hydrogen bonds of water and escape into the atmosphere. And if you kind of think back to our kinetic molecular theory of gases, we had this diagram here where our average and root mean square speeds were up here, sort of the typical speeds of gases in a sample. But say if this is the threshold energy needed to go into from the liquid to the gas phase, a certain amount of a handful of these gases at a given temperature will have enough energy. So those will break free and be in the gas phase, and that's called the vapor pressure of the liquid. Okay, so as you increase the temperature, more and more gas particles have that energy. So this line shifts. So instead of being here, if we increase the temperature, maybe that line is now, say, like right here. And then a larger fraction of those gas particles can escape up into the atmosphere. And so vapor pressure does change with temperature. But what happens, say, then if we put something like salt in there? Okay, so again, we have to have this energy, we have to be able to escape. When you start adding a solute into the solution, instead of having a free path to escape into the atmosphere, sometimes a gas particle will collide with an ion in solution. When that happens, the particle cannot make it out into the vapor phase, so you're going to get less and less of your solvent able to escape into the gas phase. So it's kind of like a barrier from allowing those water molecules to escape. Also, because they're forming such sort of strong ion dipole bonds in solution, it's preventing more water molecules from escaping as well. Okay, so our pressure of solution, so the vapor pressure of the solution, is equal to the mole fraction expressed in terms of the solvent this time, not the solute, times the vapor pressure of the pure solvent at a given temperature. Okay, so X times your pressure of your pure. Okay, so this can be calculated. We've done this. This would be given. Okay, so if you had to do a problem like this, your pure solvent would be given. You'd be able to find it in a table or be given in a problem. Okay, so what this says is essentially the more solvent you put in here, so as this gets larger, then this, or excuse me, the more solute you put in, I'm so sorry I did this backwards, the more solute you put in, the less this is going to be, and the lower your pressure of your solution is going to be. So if you put a lot of solute particles in, you're going to have a much smaller fraction of the solvent, and it's going to reduce your vapor pressure of your solvent quite a bit. Okay, so let's take a look at an example. We're going to find the vapor pressure in solution that's made with 22.5 grams of C12H22O11 that has a molar mass of 342 grams per mole in 200 grams of water, 18 grams per mole, at 338 Kelvin. Okay, so our solute here is C12H22O11, which is a form of sugar. So we're dissolving 22.5 grams of sugar into 200 grams of water. Okay, so pure water at 338 Kelvin has a vapor pressure of 187.5 torr. So that is our pure solvent here. So we're going to calculate how much of that is going to be reduced by introducing in there this sugar molecule that will prevent those gas particles from escaping. Okay, so all we have to calculate is the mole fraction. So we're just going grams to moles. So for the solvents, 200 grams of water divided by 18, 11.11 moles of water. Same thing, 22.5. They gave us the molar mass. That was quite nice of them. 342 to give us 0.0658 moles of sugar. So now we're going to put this in the numerator. We want to know how many moles of solvent we have. So our total moles, 11.18, if we add those two together. So our pressure of our solution, X, which is our solvent, divided by total, times the vapor pressure of the pure water, 187.5, gives us 186.4. Okay, so introducing in there those 22.5 grams of sugar molecules reduced our vapor pressure by 1 full torr. Okay, so the amount of water escaping into the atmosphere was reduced by essentially 1 torr of pressure. Okay, so again, as vapor pressure of the liquid is lowered as we start adding more and more solute in. Okay, so again, given with this formula right here. Okay, so our next colligative property is going to look at how boiling and freezing temperatures change when we make solutions. Okay, so let's take a look at a sort of typical phase diagram. Okay, so we learned from colligative property number 1 that vapor pressure of the liquid is lowered. So if we look at our lines separating our liquid and solid and liquid and gas or vapor, these are going to be lowered. So what that means is when we make a solution, that is going to be lowered like that. Okay, on the other side as well, it's going to be lowered. Oh, I kind of exaggerated that quite a bit. It's not quite that, but you get my point here. Okay, so what does this mean in terms of freezing and boiling? Okay, so let's look at normal boiling. So let's say this is 1 atmosphere of pressure. So normal regular conditions. Okay, so I'm going to draw a line across like that. So that represents the pressure of normal regular things. Okay, so for a pure liquid, that's right here. So this is temperature freezing of the pure solvents. Okay, so where this crosses this curve over here, this is our temperature boiling of the pure. Okay, that occurs at those temperatures, whatever those happen to be, depending on what this is. Okay, so now let's look at what happens when we make a solution. Okay, so let's look at the freezing temperature first. So if we drop that down, where it crosses now our new solid liquid boundary, we have temperature freezing of the solution. And if we look, that has lowered quite a bit. So it has gone down. So we have decreased the freezing temperature. If we look at the other side, it has crossed this boundary line right here. If we come down to find that temperature, now we have temperature boiling of solution. And we have increased this temperature. Okay, so we call this boiling point elevation. So it's boiling at a higher temperature. And we call this one freezing point depression. So it is freezing at a lower temperature. Okay, so again, I kind of drew these vapor pressure lines kind of exaggerated so we could kind of, see them very well on the graph here. It's not quite so dramatic. But again, the process is the same. You get an increase in boiling temperature and you get a decrease in freezing temperature when you make a solution. So we can quantify this. So let's look at boiling point elevation first. Okay, so we have again our phase diagram, our boiling point lowered here, and the difference here going from our boiling temperature of the pure liquid to this solution is called delta TB. So that is the change in boiling temperature, and that is the temperature of boiling of the solution minus the temperature in boiling of the solvent. So delta TB equals TB solution minus TB solvent. And that is equal to IKBM. And so what are all of these fun things? Okay, I is called the Van't Hoff factor, and that's kind of a factor of how many. And what that means is, for example, the number of particles in solution if we dissolve salt, which is an ionic compound, where when it dissolves we get an anion and a cation, is much different than if we dissolve sugar, which is a molecule and it doesn't dissociate and we just have one. So it's kind of a factor of how many. So it's not quite as easy as just adding them up, but it's a very good approximation. So for example, for NaCl, because when it dissociates you get Na plus and Cl minus, the Van't Hoff factor is about 2. Na3PO4, we get 3 Na and a PO4 3 minus, so we get I equal to 4. So that's probably not quite right, because with charges this high you would get clumping of ions in solution. So it'd probably be a bit less than this, but it's again a good approximation. And then finally, anything molecular that dissolves is going to give us a Van't Hoff factor of just 1 because it's not producing multiple particles. Okay, so next we have Kb, that is the boiling point constant. And so this would be given to you. Again, it's a constant. It would be something that you could look up in a table in your book or would be given to you on an exam. And then, of course, script M is the molality. So how the delta TB it changes, of course, is molality, remember, is moles of solute over mass of solution. So as the moles of solute increases, we're going to get a larger change in delta T. Okay, so we can increase our boiling point or elevate our boiling point more if we have more solute in solution. Okay, so we'll kind of take a look at a practice problem, but we just kind of want to kind of define these things a little bit first. Okay, so what about the opposite? Again, freezing point. So we saw this where we have delta TF. Now we're going to call that is our freezing point depression. So delta TF equals TF solution minus TF solvent equals negative, since we're depressing it, negative IKFM. Okay. So we have a different K because the slope of this line is very, very different than the slope of this line. So your KB and your KF are different constants. So this would be different. So you could look up your KF and KB for any given solvents that would be used in this class or on an exam in a table in chapter 13. Okay, so everything else is the same. I is the same I, M is the same M. This is just called the freezing point constant. Okay, so depending on what is going on, you choose this one, or if it's boiling, you choose the boiling point elevation. Okay, so let's look at an example. So we are calculating the boiling temperature, TB, of a solution for a solution made by dissolving 10.7 grams of C6H12O6 into 250 milliliters of chloroform. Well, that's fun. Okay. So we have delta TB equals TB solution minus TB solvent equals IKB molality. Okay. So let's look up these things. Our boiling temperature of our pure chloroform is 61.2. Our KB of our solvent, looking that up, is 3.63 degrees Celsius per molality. This is a molecule, so I is 1. And then the density of chloroform is 1.49 grams per centimeter cubed. So again, this would be given in a problem as well if you did need it. Okay, so if we look, we have I, that's 1. We'll plug that in. We have KB, that's the 3.63. We would plug that in there, so we have that. So we have our boiling temperature of our solvent. That goes there. We're solving for this, so all we need to calculate is M. So we're going to take this, and we're going to take this to turn it into moles. Okay, so that's the first thing I did. 10.7 grams of C6H12O6 divided by the molar mass to give me my 0.05944 moles of C6H12O6. And so that's step 1. Step 2, for molality, remember molality is moles of solute divided by mass in kilograms of solvent. Okay, so we have our 250 milliliters turning to liters, and then multiplying by the density, which I turned from grams per centimeter cubed or grams per milliliter into kilograms per liter. Okay, so to go from grams to kilograms is a factor of 1,000. To go from milliliters to liters is a factor of 1,000. So this can be in grams per milliliter or kilograms per liter. But again, if you aren't aware of that, or if you don't know that, you could turn these milliliters, you could take this milliliters, you can use this here, and then turn it into kilograms when you're finished. Either way would be fine. Okay, so we got 0.373 kilograms of solution. Okay, so the last part here is we just need to plug it all in now. Okay, so let's plug it in. All right, so our TB of solution minus our 61.2 degrees Celsius, again, just plugging things in, our Van off of 1, our KB of solution, 3.63 degrees Celsius kilogram per mole, and now we're solving for our molality. We're plugging in for that. So our moles, the 0.05944 moles, divided by our mass of chloroform in kilograms, 0.373 kilograms, which gives us this. So we get TB of solution minus 61.2, multiply and divide through to get the 0.579 degrees Celsius. So this is our, again, remember this whole thing here is delta TB. Okay, so again, remember all of this is delta TB. So our boiling temperature was elevated by about a little over a half of a degree Celsius. So sometimes you're asked to solve for just your boiling point elevation. That's the delta TB, which would be this here. So we're asked to find the new boiling temperature of the solution. So we're just going to add this over to get 61.8. And so again, it increased, little over a half of 8 degrees Celsius, our boiling temperature, by adding in that C6H12O6 to that chloroform there. Okay, so it is a matter of just plugging things in. The only thing we really usually have to solve for is the molality. Okay, so again, most of the time you're given grams of your solute. So a lot of times you do have to turn that into moles. So super fun practice of, grams divided by molar mass. So there. And then you need the mass. So again, we had to use the density again to turn the milliliters into mass. So kind of some fun practice using maybe some density types of things that we haven't used in a while. Okay, so plug it in and solve. Okay, so our last topic that we're going to see, last colligative property is called osmosis. So osmosis is movement of solvent molecules across a semi-permeable membrane from low to high solute concentration. So this one we're looking at the movement of solvents. Okay, so I have this drawing here of a solution. So we have high concentration of solute here, low concentration of solute here. So what's going to happen over time is the solute, the liquid, is going to move across the membrane. So we'll draw an arrow. So solvent is going to move across. Okay, so if we have the liquid in this side moving across, over time this is going to be lower in volume. If we have the solvent moving across, this is going to be higher in volume. Okay, so we'll still have our particles, but now we have a much larger volume here. Okay, so this was at much lower concentration here. So as time passes, the concentration of this one went up. So the molarity of this one went up because our volume went down. But this one here, these ones are all really, really tightly packed together here, and now we have a much larger volume. So for this one, we had a decrease in concentration or in molarity because the volume went up. Okay, so that's what we're looking at here, movement of the solvent. So this is very, very important in biology, where you're looking at, cells, and if your concentration of, solute particles is not quite right, when you look at your cell as opposed to the rest of the environment, you can have cells exploding and shriveling up due to having, too less or too much of a concentration of different solute particles in there. Okay, so we look at how things are going to move across this semi-permeable membrane by looking at what's called osmotic pressure. So osmotic pressure is capital pi equals IRT. Okay, so pi equals IRT. Oh, I'm missing something. IRT times molarity. I forgot the M. So we'll squeeze that in. Oop. M, molarity. Okay, so pi equals IRT times molarity. That's very important there. Here, we'll write it even better. Pi equals IRT times molarity. Okay, so what this osmotic pressure is what sort of pressure we would have to apply here. So what pressure we would have to apply here to force the solvent back this direction and make the liquid levels equal. So what pressure we would have to apply, force the solvent molecules back, make the levels equal, and that is the osmotic pressure pi. Okay, so for example, we have 3.4 grams of NaCl per 1 liter of water at 20 degrees Celsius. So that's what we have here. So on one side of our apparatus here, we have pure H2O. On this side, we have that 3.4 grams in 1 liter. Okay, as time passes, since there's, no solute over here and lots of solute over here, we're going to get the water going this direction through the membrane from low concentration to high. So over time, this level is going to drop and this one will go up. So we're making this much less concentrated. So again, the osmotic pressure would be what pressure do we have to apply here to make these two levels equal. So pi pressure to make levels equal. Okay, so we solve by using this here. All right, so pi equals, so we have I is 2 because it's NaCl, so we get a sodium and a chloride particle, so that times R, 0.08206 liter atmosphere per mole Kelvin. Temperature, in this problem, 20 degrees Celsius, which is 293 Kelvin. And then molarity, okay, so 3.4 grams of NaCl. If we divide that by the molar mass, it's 0.05812, and that's per 1 liter. So that's the one right there. So that's our molarity, moles of this per 1 liter of water. So 2 times R times molarity times temperature. If we look, because this is the fun part, right? Liters cancels with liters. Moles cancels with moles. Kelvin cancels with Kelvin, and we are solving for a pressure. Okay, so our pressure, our osmotic pressure is 2.8 atmospheres of pressure. Okay, so it does kind of seem weird, like why would we use the gas constant in a liquid? That's not a liquid. If you think about a gas is something that is a very tiny particle in a very large volume of space. If you kind of consider a solute is not that far from that. It's a piece of NaCl, so a small amount of NaCl in a very large volume of water. Okay, so not quite exactly like a gas, but very similar to it in that, again, a large volume with a very, very small particle. Okay, so that is the end of the colligative properties and the end of things from chapter 13. Again, concepts not huge. It's mostly just a lot of practice using your chapter 13 formula here. Okay, so you can add, we went through using all of these. We only used one of these here, but that's okay. You can add here if you like. The one that is missing, I should probably update, is number 9, that your osmotic pressure equals IRT times molarity. Okay, so your Van off, your gas constant, temperature, and molarity.